All right, good morning, everybody. I hope you all are having a great week and surviving the cold weather. Couple quick announcements to get us started. So if you were not able to attend one of the algebra reviews, but you would like to see that video, it's now posted under Getting Started. So the lecture video from those Zoom sessions is posted, so you can go over that if you needed some extra help brushing up on the algebra. There will be another review session on Thursday of this week and Monday of next week on graphing. I'll talk a little bit more about that on Thursday, but that's the next topic that is going to be reviewed during those review workshops. So today we're going to be covering we're going to try to cover 3 different topics. We'll see how much we get through. But again, this is review, so we're going to go a little bit faster than we normally would for stuff that is not a review. And if there's stuff that is not making sense or whatever, you can definitely come to Drop In Help. I always encourage you to read the textbook sections of the things we're covering. They're usually only 2 to 3 pages, or you can watch the lecture videos if you want to see the examples done out again or more thoroughly, things like that. So we're going to be talking about economics and what that means and the different types of things there. Then we'll talk about exponential functions, and we may or may not get through that and get to the natural log, which is just a process that we're going to be using algebraically. So if we don't get through that, definitely feel free to watch the asynchronous video if you don't remember. You might completely remember and not need that at all. So it really just depends on when you last saw it. So let's go ahead and switch over to the DocCam. Okay. So this course is designed to serve 2 sort of groups of majors. There's the life sciences and the social sciences. And in the social sciences, we really focus on the business aspects. So we think about how businesses work, how economics work, how those work together, and how we can think about those calculus. So in order to be able to do those types of applications later, we need to sort of lay the foundation of the different things we'll be talking about now, because not everybody has taken an economics class or has worked with these types of things. So A lot of this is going to be background on definitions and how these things look, but we will be using these throughout the course. So this first section, applications of functions to economics, it's called that. It's really business applications. So if you're going into any sort of business, this will be relevant to you. So we're going to start by talking about what different types of functions mean in the world of economics so we can understand sort of how to think about them. So the first one that we're going to talk about is the cost function. So the cost function, which we're going to call capital C of Q, C is for cost, Q is for quantity, is going to give us the total cost of producing Q items of some good. So when we think about cost, we're thinking about it from a manufacturing standpoint. How much does it cost me to make this product that I'm going to sell? Okay. So this can be easily confused with price, which is the cost of an item when you sell it. And these are two different things. So when we think about cost, it's how much it costs to make an item or produce an item. So as we talked about last time, right now, we're assuming the thing that we know is linear functions. That's sort of where we're building on to. And so when we start talking about these applications, we are also going to assume that for now, things are linear. In chapter 2, we'll say, hey, what if they're not linear? But for now, we're still going on this like linear train, right? So for a linear function, usually we have y equals mx plus b. If we're using the variables that we're talking about here, we have c of q equals mq plus b, something like this, right? So q is our variable here, not x, and c for cost. So cost has two parts to it, right? And the first part is called fixed cost. That's our B. So that's the cost even if nothing is made, okay? So if Q equals 0, that value is your fixed cost. And so why would we have fixed cost? So let's assume that you are going to be making tennis rackets, right, to sell. So you might buy a machine that strings the rackets, okay? So that is a fixed cost. That is something you buy once, and before you've even made any tennis rackets, you've invested that cost. It's a one-time cost that does not depend on the number of items that you're making, okay? So there's a lot of things that could fall into that category. You could buy a warehouse to build your stuff. You could buy a special machine, right? Things that are one-time costs. The second type of cost is variable cost. So this is the cost that depends on how many units you are making. So if you are making tennis rackets, variable costs would be things like, you know, the string for the racket, the paint for the racket, the grip for the racket, the actual metal for the racket, right? The amount of money you spend on those materials depends on how many you are making. And so that cost is our slope, okay? So variable cost, okay, is represented by the slope of the line. Now, one of the things that we talk about a lot in our business examples is how much does it cost to make one more, right? What's my additional cost going to be if I make one more tennis racket, right? I want to see, you know, that what's called on the margins, what my additional cost is going to be. So we introduced this idea of what's called marginal cost. So marginal cost is the cost to make one more. And so for a linear function, that is also the same as variable cost. It's the slope, right? If you make one more, your cost goes up by that slope amount. So for now, our marginal cost is going to be the same as our variable cost. And that's true for linear functions, which is what we're working with right now. So let's look at some examples of cost, how we think about it, what it means, and all of that. So consider the two following scenarios. So we'll start with part A, then we'll do part B. We want to draw a graph of a linear cost function that satisfies the given conditions. So I want you to try to sketch a line, a linear function, that represents the story that fixed costs are small, but marginal cost is high. Okay, so think about which parts of the equation this talks about and what a linear function with these characteristics would look like. Okay, so just take about 30 seconds, just draw a quick axis, and then think about what your line would look like. Okay, so a couple things we really need to think through to make sure we understand sort of the reality of what's happening. First is that our slope of our line is always going to be positive, right? Things are not going to cost less. Like you can't have a negative variable cost because that's for like materials. So that means that no matter what we're doing, our M is always going to be positive because it doesn't make sense for it to not be. Okay, so again, our B has to do with our fixed costs, right? Because if Q is 0, then our B is our fixed costs, and our M has to do with our marginal or variable cost, because again, those are the same in a linear function. So here, fixed costs are small, marginal cost is high. What does it mean for it to be small, right? Fixed costs are small. That means our plus B is small, which means our plus B is where we cross through the vertical axis. In order for it to be small, that means we want to be on the lower end of our axis when we cross through. There's no particular right answer, but really you should be crossing through somewhere in the lower part of the vertical axis. So I'm just going to pick right here, right? So you could have picked somewhere here, here, right? These are all small places to cross through. Now, we also know that the marginal cost is high. Okay, when we talk about something being high, that means large. We have a large slope. Okay, when your slope is large, that means that your line is steep in the positive direction. So we want to go up quickly. So we might have something like that. Yours might be a little bit more steep, right? It might be over here, that's fine. But it should definitely be higher than sort of the y equals x slope line, right? So like the top half of this triangle, if we were to cut it in half, somewhere in this range, right? So again, small means low. If we have something that's high, that means we're steep when we're talking about slope. Okay, let's try another one. So here I want you to sketch a cost function where there are no fixed costs. So fixed cost is 0 and marginal cost is small. Okay, so again, just quickly sketch if you have this printed out, do it on this. If not, just draw an axis and then draw what that linear cost function might look like. Okay, hopefully you have a good guess here. So if there are no fixed costs, that tells me that B equals 0. So that means when I cross through this vertical axis, I'm crossing through at 0, 0. Marginal cost is small. So slope is not steep. Okay, so we should be in the bottom side of this triangle. So something like here, right? Oh, can you guys see that? That's kind of not that dark. Let me try to darken it. Right, so we're still increasing because we still have some marginal costs. It just happens to be small. So the slope should be shallow, something like that, something, you know, in that general idea. Okay, so thinking about how we describe things without numbers helps us understand how to visualize and build models. So when you hear words like no fixed cost, that gives us a 0 interpretation, right? B equals 0. Marginal cost is small, means slope is not steep, right? It's a small number, which means that when we're talking about magnitude, right? Steep is high, small is shallow. Okay. So that's just some examples of how some of the wording comes up in these types of problems that you just want to be aware of. So now we want to think about setting up equations. So here we have a company that's going to produce ceramic pineapples. The cost to purchase the molds in the kiln is $20,000, which are incurred even if no pineapples are made. The cost of labor and raw materials are variable costs since these quantities depend on how many pineapples are made. The variable costs are $6 per pineapple. Assuming that the cost is linear, I want you to set up an equation using the information from the problem for this cost equation. And then B, determine the marginal cost from the information or your equation, and just explain what it means in this context. So what does it mean in terms of cost and when we're talking about pineapples? Okay, so take about 2 minutes, maybe 1 to 2 minutes, set up your equation, and then see if you can determine the marginal cost and what it means. Okay, then we'll go through it together. Okay, take about 30 more seconds. All right. So we want to use what we learned in the setup of the problem to figure out the associated parts. So we know that we need a variable cost and a fixed cost. The fixed cost here is going to be the $20,000 because that is the cost when we haven't even made any yet, right? It's the pineapple molds, it's the kiln, and it's incurred even if we haven't made any. So our fixed cost here is $20,000. And then over here, our variable costs, and it even says variable costs, are $6 per pineapple. So we have 6 times Q. So if we make 1 pineapple, we have 1 times 6. If we make 2 pineapples, 2 times 6, right? But no matter what, that 20,000 is incurred. So our model looks like this from this setup up here. So 6Q plus 20,000. Part B is to determine the marginal cost and explain what it means in this context. So again, as a reminder, if your function is linear, your variable cost and marginal cost are the same thing. So the marginal cost here is $6. And what that tells me is if I make 1 more pineapple, my cost will go up by $6. Okay, so it's the additional cost to make 1 more pineapple. So something like this, right? So that's what it's going to mean in this particular context. Okay, so that's cost. So hopefully that makes sense on what we're thinking about. The next part we want to talk about is called revenue. Okay, I don't know why it says this. Ignore that part. Okay, so revenue also we're thinking about from a manufacturer standpoint. So now we're thinking about, okay, we know how much it costs to make this product, but how much money can I bring in if I sell my product, right? So this is like the other side of the coin for our manufacturer. So revenue functions, which we're going to notate R of Q, R for revenue, Q for quantity still, is going to be set up again as a linear function, okay? And so the amount of money that you bring in is going to be the price that you charge times the quantity that you sell. So P times Q, okay? Now, here we have to remember that Q is our variable. So price is going to be some sort of constant, and it's the selling price. So it's really easy when you're reading problems that are a little bit longer to confuse things with cost having to do with price. So just try to file away that when we talk about price, it's how much we are selling something for in a scenario, okay? So if we're thinking about selling a good for $5, our revenue function would be 5Q. If we're going to sell it for $30, it would be 30Q, so on and so forth. And just like before, this is a slope, right? We don't have a plus B here because if we don't sell anything, we don't make any money. So there's no plus B. B is 0. But what I want to mention is that slope is also referred to as marginal revenue. Okay, so just like before, we had marginal cost. If your revenue is linear, then the slope, which is the price, is marginal revenue. So it's the additional revenue from selling one more. Okay, so let's look at some examples of how this comes up and see if we can get these set up. So I'm gonna let's do 2 examples. We'll do them all together. So example 3 says, suppose I've decided to open a store that sells gourmet cookies for $9.99 per tin. Set up a revenue function for my sales and determine my revenue if I sell 221 tins of cookies. So the first part, you're setting up the general revenue equation using price times quantity. And then the second part of this one, you're figuring out what the revenue is if quantity equals 221. So that's the first part. And then you're also going to try example 4. So suppose that ceramic pineapples, just like the ones we were making before, are sold for $20 each. Find a formula to represent the revenue function. So how do we set it up with price times quantity? And then sketch the manufacturer's revenue function below. So once you have your revenue function, I just want you to take a minute to graph it and think about what that graph looks like on this axis. Okay, so for these 2 problems, I'm going to give you 2 to 3 minutes, see what you can work out. The key is really setting up the revenue function for each of them. That's like the big picture thing we want to do. So if you can get that done for both of them, that'll be great. So take 2 to 3 minutes and then we'll go through them together. Okay, take about 30 more seconds. All right, so let's make sure we have these set up and that we can solve things with them. So for example 3, we have this tin of cookies that we're selling for $9.99 per tin. That means that my price here is $9.99. So my revenue function is going to be $9.99 times Q. So every time I sell a tin, I get an additional $9.99 in revenue. So this is my general function. And now the second part wants to know, what's my revenue if I sell 221 tins? So that means I need to plug in 221 for Q. And if I plug that in, I put that in my calculator, I'm going to get $2,207.79. Okay, so if I want to know my revenue at a certain quantity, I just plug it into my revenue function. A couple quick things about units here. So cost and revenue, we're talking about money. So we have the dollar sign. If you have decimals longer than 2 decimals, our currency system is set up to have 2 decimals. So we always round to 2 decimals unless we're told to round to like the nearest dollar or something. So it's always 2 decimal places with money. Okay, so that's number 3. For number 4, we have ceramic pineapples, and we're selling them for $20 each. So that is our price here. So our revenue is 20 times Q. We want to find a formula to represent it. That's our 20Q. Then sketch the revenue function below. So if we want to sketch this, we just need 2 points on our line to connect it. So you can use any 2 points. I chose 0 and 5. So when quantity is 0, revenue is 0. So I have 0, 0. And then when quantity is 5, revenue was 100. Again, you can plug in any 2 numbers to get 2 points. And then we just connect the 2 points with a line the best we can. And it just keeps going up. The more we sell, the higher we go. So that's what our revenue function looks like if we were to graph it. So if we were given a picture of revenue instead of an equation, we would be able to set up the revenue equation by finding the slope of the line, and then we would know the price. Okay, so that's revenue. That's sort of the second piece of our business puzzle. And then the third piece, which is probably the part that you would see most if you go into business and economics, is profit. So profit is looking at the relationship between revenue and cost. And so profit, we use the pi of Q. We don't use P for profit because we use P for population quite a bit in math. So we use pi instead. We use lowercase pi. And profit is going to be revenue minus cost. So the amount of money you take in from selling an item minus the amount of money you spent to make the item, right? So revenue minus cost is going to give you your profit. So a couple things. One, profit can be negative. If you spend more money than you make, then your profit's in the red, is what we call it. And that is negative. And that happens all the time for businesses at the beginning, right? Like if you've laid out all this money to start your business, you have to get to a certain level before you actually have positive profits. So one of the things we often look for is what's called the break-even point. So the break-even point for a company is the point where the profit is 0, and that happens when revenue equals cost. So when the profit equals 0, that is the point where if we make one more, we become profitable, okay? And again, we're really just thinking about, simpler functions right now. We will elevate this to harder functions later. But if profit equals 0, so profit is revenue minus cost. The break-even point is when profit equals 0. You can see that if we were to add the cost over, this is the same thing as revenue equals cost, right? So when those things are equal, the amount of money that you've spent is equal to the amount of money you've brought in, you have broken even. And theoretically, if you sell more from that point, that's when you start making money. And we use the word profitable to talk about when you start making money, okay? So a couple quick things. When you set up a profit equation and you do revenue minus cost, you need to make sure you subtract off the entire cost function. So most of the time, cost has more than one term, which we'll see in our example. So you want to use parentheses for your cost function so you don't lose the negative on any of the terms. Okay, so here's an example. We want to find a formula for the profit function for the ceramic pineapples manufactured in the previous examples. We want to graph the profit, and we want to use our algebra to mark and find the break-even point. So as a reminder, the cost function for our ceramic pineapples was 6Q plus 20,000. Variable cost was 6. Fixed cost was 20,000. Our revenue function, our revenue function was 20Q. So we're selling them for $20 each. Okay, so I'm going to give you 2 minutes. I want you to set up your profit function, being really careful with negatives. I want you to graph your profit function, and I want you to mark on this profit function the break-even point and determine it algebraically. Okay, so see what you can figure out, try it out, take two-ish minutes, and then we'll go through it together. Okay, take about 30 more seconds. All right, so to set up our profit equation, again, we're going to do revenue minus cost. My revenue here is 20Q minus, now my cost has more than one term, so this is where I was recommending you use parentheses. So 6Q plus 20,000. And I'm going to take one step just to combine like terms. So I have a 20Q and a minus 6Q. So that's going to give me 14Q and then minus 20,000. So that's my simplified profit equation. And so I want to graph the profit. So I'm going to graph this function. If you subtract two linear functions, you're going to get another linear function. And we want to mark the break-even point. So when I look at this equation, I see that my vertical intercept is at negative 20,000. So that means when I start off, I'm making a negative profit. So I'm in the hole, okay? But my slope is 14Q. I'm positively sloped, and I'm going to be going up through here at 14Q. Okay, so we have a function that looks roughly like this. Okay, so we have an upward sloping function, and we really want to know, where do we break even? So the break even point is when profit equals 0. Profit is going to equal 0 when it crosses through the x-axis, or the q-axis here, I should say. Okay, so anywhere below this quantity, we're in the red. We're not making any money. right? We have negative profit. But once we cross through, we are now positive. We have a positive profit and we are profitable. So this is the exact point where we change over. How do we find that point? Well, we can take the algebraic function and set it equal to 0. Right? So we add the 20,000 over. Okay, we divide both sides by 14, and we get 1,428.57. Okay, we need to talk about this because this is sort of an awkward number because Q is quantity. And so it doesn't really make sense that we're making part of an item. So we need to talk about when we're profitable and when we're not. So if we manufacture 1,428 items, we are still slightly in the red. We are still slightly negative if you round down to the nearest item. If you manufacture 1,429 items, you are now slightly in the positive. Okay, so we can't just round to talk about the break-even point. If you round down, we're still in the negative. If you round up, we're in the positive. This is the exact quantity we would have to make to break even. And so most of the time, the question will say something like, how many do you have to make to be profitable or to make money? And so then we know that we have to round up to 1,429. But the exact number to make this work mathematically, right, is this point here where quantity is 1,428.57, which we can all agree is a little awkward. And at that exact point, our profit is 0. So anything above that, we're making money. Anything below that, we're losing money. Okay, so profit, again, we're really thinking about this relationship between revenue and cost. If revenue is bigger than cost, we are making money. If it's lower than cost, we're losing money. Okay, so let's think about if we have some data and how we might interpret that to think about profit. So the table below shows the cost of manufacturing various quantities of an item and the revenue that is obtained from their sales. So here the quantity is across the top and then cost and then revenue. So for example, if you make and sell 40 items, it's going to cost you $1,000 and you're going to bring in $1,200. That's what that table is telling us. So for part A, I want to know what range of production levels appears to be profitable. So I want to remind you that the word profitable means positive profit. Okay, so we're actually making money. That's what profitable means. For part B, we want to calculate the profit or loss, so how much money we're making or losing for each quantity shown. This is the same table. There's just an extra row for you to fill in. Okay, then we want to estimate the most profitable production level. So when is profit the most after you've calculated all of these things? It might make sense for you to do part B first and then part A, since they're kind of related and you're going to have to kind of compare them anyway, but it's really up to you. So I want you to take 2 minutes, try it out, see how you might answer these questions and think about these ideas of cost, revenue, and profit and see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. All right. So for part A, in order for us to be profitable, we need to be past the break-even point. Okay, so just as a reminder, profit is revenue minus cost. And in order to be profitable, we want the profit to be greater than 0. So if revenue minus cost is greater than 0, that tells me that we are looking for when revenue is greater than cost. Okay, so for each production level, we can compare revenue and cost to see when it's bigger. So 0 is not bigger than 120, 300 is not bigger than 400, 600 is the same as 600. We'll come back to that. 900 is bigger than 780. 1200 is bigger than 1000. 1500 is bigger than 1320. 1800 are the same. 2100 is not bigger than 2500, and 2400 is not bigger than 3400. So something interesting happens on this table where we see that there's two places where the cost and revenue are the same. And so we said before that when that happens, that is the break-even point. Okay, so we break even at Q equals 20, and again at 60. So what this is telling me, since it happens twice, is that this particular set of cost and revenue are not linear. So I'm not going to be talking about marginal revenue and marginal cost because these are not linear functions. So since I am profitable between these two break-even points, it's reasonable to say that I believe that I'm going to be profitable between 20, where I first break even, and 60, where I then stop breaking even. Okay, and so in between them, I'm not going to use the equal signs because at that exact point it's 0, but it seems like between those 2 points, my revenue is greater than my cost. Okay, now for part B, we're going to be calculating the profit and loss at each point. So in order to calculate the profit, we're doing revenue minus cost. So for each point, I'm going to go ahead and do revenue minus cost. So 0 minus 120 is negative 120, right? 300 minus 400, negative 100. 600 minus 600 is 0. 900 minus 780 is positive 120. 1200 minus 1000 is 200. 1500 minus 1320 is 180. 1800 minus 1800 is 0. 2100 minus 2500 is negative 400. And 2400 minus 3400 is negative 1000. So I have the profit or loss for each quantity. And the second part of the question says, estimate the most profitable production level. So most profitable means that not only is my profit positive, it's the largest positive profit that I can find. Okay, so I'm only considering positive profits. And if I look between them, 200 is the largest one I see. So to answer this question, the question is the most profitable level. That means I'm looking for the quantity that makes the most profit. So I'm looking for this 40 here. Okay, so production level is quantity. Okay, I could have asked you to estimate the largest profit, then the answer would be 200. The profit level is the 40. So those nuances in how we word the question is going to make a difference on which number you use to answer the question. Okay, so as I mentioned, we talked a lot about this sort of idea about being on the margins. So our next problem, we're going to sort of tie all this together and think about what margin really means. So just like we talked about marginal cost to talk about the slope of a cost function, we use marginal revenue and marginal profit to talk about the slope of linear revenue and profit functions. So whichever function you have, cost, revenue, or profit, if it's linear, then the marginal cost, marginal revenue, marginal profit is the slope. And again, marginal is asking the question, if I change by 1 in the independent direction, how does the dependent variable change? And so that is the definition of slope for a linear function, right? We will come back to marginal sort of analysis once we deal in nonlinear functions, but for now we're considering the slope to think about how it changes. Okay, so for example 7, there's a whole set of questions that sort of tie in all this ideas of evaluating these different functions and how they work. So I want you to try this out. You're given a cost function and a revenue function, and then you're asked questions like, what is the fixed cost? What is the profit, right? So when we're talking about profit, we have to find the profit function first. So I want you to try this set of questions. There's 6 questions that sort of are all tied together. Some of them will hopefully be pretty straightforward, and some of them you might have to do a little thinking and putting things together. But I want you to take 2 to 3 minutes and see what you can figure out. Feel free to bounce around. You don't have to do the questions in order. You can do the ones that you feel really comfortable with and then go back to others, but then we will go through it together. And as always, feel free to check in with someone next to you or ask a TA if you're stuck. Okay, so take 2 to 3 minutes and then we'll go through it. Okay, take about 30 more seconds. All right, so just as sort of a good anecdote here, I just want to say, if you don't have enough time to finish the problem we're working on in class, that is totally fine. I am not giving you as much time as I would want you to spend on these because we have to get through a lot of material. So if you're feeling like, oh, I can only get through 3 parts when there's 5 parts, that's totally normal, just because we don't have enough time in class to sort of give you all the time that I wish I could give you. So I don't want you to feel like that's an indication of how well you know something. The idea is that I want you to think about how to get started and then do the things that make the most sense to you. And then we sort of fill in the gaps as we go. Okay. So part A, what is the fixed cost of this product? So to find fixed cost, we need to go to the cost function, which is given up here. And remember, there's two parts. There's fixed cost and there's variable cost. And fixed cost is the cost when quantity equals 0. It's the plus B. It's the part that you pay for even if you don't make any. So here, that's going to be our $8,100. Okay, because that is not dependent on the variable. It's a standalone number. Part B, what is the marginal cost? So again, with a linear function, marginal cost is the same as variable cost, which both represented by slope. So if we go here, we see that the slope, which is the number tied to the variable, is $4.45. Okay. For part C, what is the price this item is sold for? What is this called? So price, I want to remind you, has to do with revenue. So the price is part of the equation of revenue, which is price times quantity. So we want to go to the revenue equation, and then we want to look at what the P is that has been substituted in, which is $5.65. And again, because revenue is linear, this $5.65 is the slope, which we know represents the marginal revenue. Okay. So part D is now talking about the profit. What is the profit when Q equals 1,000? Well, in order to answer this question, we need to set up the profit function. We don't actually have that yet. So as a reminder, the profit is going to be revenue minus cost, right? So our revenue function was 565Q minus our cost function, and again, I'm going to use parentheses because there's more than one term, was 8,100 plus 445Q. Okay, so revenue minus cost. So I'm going to take it one step further, and I'm going to simplify this equation by combining like terms. So 565Q minus 4.45Q is going to be 1.20Q. You can also write it as 1.2Q. That means the same thing. Okay, minus 8,100. So again, the minus goes to both terms. So now I have a profit function. I want to know the profit when Q equals 1,000. So I'm going to plug in a 1,000. And unfortunately for this product right now, we are going to get negative 6,900. So if I make and sell, oops, that second zero looks goofy. If I make and sell 1,000 of this item, I'm going to be in debt negative, or in debt $6,900. My profit is still negative, right? So the next question, which makes sense given that this is negative, is what level of production does this company need to reach to make a positive profit? Okay, so we're kind of thinking it's probably going to be more than 1,000, because at 1,000, we were still pretty negative. So in order to figure out when we're making a profit, we first need to figure out where we break even. And once we know where we break even, we make a profit by adding one more, right? Going to the next whole number. So to find the break even point, we want to take our profit function, which was 1.2Q minus 8,100, and ask the question, when does that equal 0? Right? When do we break even? So we bring the 8,100 over. We divide both sides by 1.2, and we get Q equals 6,750. Okay, so that is the break-even point. However, this question didn't ask us for the break-even point. It asked us how many we need to make to be profitable. So remember, we have to go to one more than the break-even to see a positive profit. So Q equals 6,751 to be profitable. Okay, so we had to get to the break-even point, but then we had to go to the next whole number. So finally, part F, when this company produces and sells one additional item, what is the marginal profit? So again, we go back to our simplified version of the profit equation, and marginal profit is the slope of the profit function. So we have $1.20 per item. So that marginal profit tells us that for each additional item I make and sell, my profit increases by $1.20, right? So we had to make a whole lot to make up for the starting fixed costs. So that's how we figure out marginal profit, okay? So that's just sort of tying together all this idea of marginal and relating it to the slopes. The last thing we want to talk about for economics is something called a depreciation model or a depreciation function. So this is sort of related, but slightly different. So we just want to make sure that we've gone over one to see how we can put this together. So the depreciation formula is going to give us a value, which we usually notate as V of T in dollars, of an item as a function of the number of years T since the item was purchased. We assume that the value of the item depreciates linearly. So the most common example of this is a car, right? If you've ever heard like, oh, your car loses value as soon as you drive off the lot. The idea is that over time, this item is worth less and less, right? And so what we're doing here is we're saying, okay, most machinery depreciates linearly. So if we can figure out its value at two different points in time, we can come up with the linear function and then use that to figure out the value at any point in time. And this can be for any sort of big machine. So cars, refrigerators, washing machines, things like this. So here again, we're talking about value of an item. So this is why it's sort of related. So let's look at this example together. I think if we do one, you'll have a pretty good idea of how these work. So suppose that the ceramic pineapple manufacturer has a machine that costs $16,000 and is sold 10 years later for $4,000. We say the value of this machine depreciates from $16,000 today to a resale value of $4,000 in 10 years. We want to find the linear function, V of T, that represents the depreciation of this machine. Now, because the value is decreasing, that tells me that when I do a depreciation model, the slope should be negative, right? My function should be going down from left to right. So how do I find, right, the linear function for this? Well, what I need to do is I need to take what I know about the value at different time points. So 16,000 today, 4,000 in 10 years, okay? So what's varying here is time. So I have 2 points. I have the point 0, 16,000. So that's how much it's worth at time equals 0, right? How much it's worth today. But I also know that at time equals, at time equals 10, so 10 years later, the value is $4,000. So I have 2 time points, and I know the values at those time points. So if I have 2 points on the line, I can use that to find the equation of the line. So I start by finding the slope, which is the change in y over change in x. So I do 16,000 minus 4,000 over 0 minus 10, and that gives me negative 1,200. So my slope is negative 1,200 times t, so time is our variable here. And then I need to figure out what's my b. So just remember, b is your value when time equals 0. We actually already have that information from one of our points. So my b here is 16,000. If we didn't have this particular point, we could get b by just plugging in any of the points we were using. You'd plug in the value for v, time for t, and solve for b. Okay, so the depreciation model here looks like this. But again, for any of the depreciation models that you'll work on, we're just finding a linear equation and using our information points to find the slope and then the b, and then we have our model. Okay, it's a good idea to just check if you plug in one of your points. If you plug in 10, make sure it equals 4,000 to make sure you didn't, mess something up in the algebra. But that's sort of the whole thing. Okay, so that's depreciation, setting up a linear model, and you'll see the word depreciation, and that's sort of how you know you're doing this. Okay. The next thing we're going to talk about, we're going to switch gears and we're going to talk about exponential functions. So before we do that, just as a quick recap in our economics, the main ideas are cost, revenue, and profit, how they interact. I sent out an email. If you are not familiar with the concept of supply and demand, you should watch that short video. It's just sort of what's going to happen in the background for some of the work we do. Supply and demand comes up a lot more in Math 128, but there are some short videos just explaining what that means if you've never heard that before. Okay, so now we're going to talk about exponential functions. So I want to distinguish exponential functions. So before we even talk about that, I also want to include the word polynomial. So a polynomial function has x in the base and some number in the power, right? So some examples are things like x squared, x to the fourth, x to the 10th, right? These are polynomials where the variable is in the base, okay? We are going to be talking about exponential functions. And when we talk about exponential functions, what makes them exponential is that the variable is in the power. Okay, so it sort of switches positions. And one of the most important things about exponential functions that you're going to need to do is recognize that it is an exponential function. So you are looking for where the variable is. If it's in the power, it's an exponential function. If it's in the base, now we're talking about polynomials. Okay, so an exponential function is any function where the variable is up in the power. Okay, and when we talk about that, it's important to remember what's a variable and what's a constant. So the variable is what's up in the power, and k and a are constants. What does that mean? That means they're numbers, right? That might be, k might be 5, k might be 100, a might be 1, 1.5, things like that. But they are numbers, and the variable is what's up in the power. This is the most generic form of an exponential function. And I'll talk about other ways we're going to see this and more likely ways. But the first thing I really want you to do is just make sure you're comfortable plugging things into exponential functions. So if you have your calculator with you, I would like you to take it out and just try one of these. I want you to plug in t = 3, just to make sure you're comfortable with the syntax of plugging that in, because you're going to be plugging in a whole bunch when you're doing homework and computing things. You don't need to do them all, but just take a minute if you have your calculator, try one, make sure you can plug it in. I'm going to write the answers here, and then I'm going to show you in a minute on my calculator what that looks like in case you don't have yours with you. Okay, so real quick, as we're plugging things in, if we look at the first one, we have 2 times 3 to the t. So we start with the 2 and then the multiply and then 3. And then you need to use this caret button up here, right, to get it to go up in the power. Here we're plugging in a 3 for t. So we plug in a 3 and hit enter. That's how we get our 54. So we need to use that caret button. The next 2 are similar, so you can try those now or at home. But then the last one I want to talk about as well, because we have an E. So we have a 2, so we start with 2 times. Now the E button for me is behind the natural log, okay? So I have to go second, and then I have to hit the ln button, and that puts the E in for me. And when it does that, it moves the blinker to the power so that I can just plug in whatever number I'm looking for. Okay, so that's just sort of what it looks like. Plugging things in sometimes is where students get things wrong because they just aren't getting it set up right, but you should be able to see that you're plugging in a power somehow on your calculator. Okay, so you want to make sure you practice and are comfortable plugging things into exponential functions. But what are we doing with them? Why do we use them? Right? Why do we need to review them? So exponential functions we use quite a bit to think about how things grow and decay. So this comes up quite a bit in the physical sciences. So things like carbon dating is decay. We think about reactions in chemistry and catalysts and how they decay. We think about how populations grow. We think about the spread of disease and how quickly it spreads and grows. So growth and decay comes up quite a bit in the life sciences, and so that's why we want to pay particular attention to it in this particular class. So the general exponential function, when we're talking about growth and decay, right? So here we just have functions out of context, right? But when we're talking about growth and decay, you're often going to see the equation written like this: P equals P naught A to the T, okay? Which is an exponential function because T is our variable, so it's in the power. T is the most common variable because usually we're looking at what happens over time, so T for time. And so we need to pay particular attention to what P sub 0 and what A mean for like when we're talking about growth and decay. So P sub 0 or P naught, okay, this is your initial amount. Okay, usually this is a population, but it doesn't have to be. It could be like bacteria. But whatever this number is here, this is the amount that you're starting with in your measurement, right? Because if time equals 0, when we start measuring, this whole term turns into a 1. So this is the amount we're starting with, right? This P naught. And then the A, it's tricky, this little base number, A equals 1 plus R, where R is the growth rate. Okay, so the growth rate can be positive if something's getting bigger, but the growth rate can also be negative if something is decaying. And that is sort of counterintuitive because we're using the word growth, right? But R just represents like how much we are changing in the positive or negative direction. So if we are growing, then your R is positive, which is going to make your A greater than 1. Okay, so if A is greater than 1, we are growing, and your R is positive. If, however, your R is negative, that means that your A is going to end up being between 0 and 1 because you are decaying, and so your R is negative. Okay, so you can't, well, you could, but we don't really look at cases where A is negative because that would mean your growth rate was more than 100% decay, which doesn't make sense for the things that we're going to be looking at. So your A will always be positive, but what matters is if it's between 0 and 1, so a decimal, or greater than 1. Greater than 1, we're growing. Between 0 and 1, we are decaying in whatever we're measuring. So linear functions, which we've been talking about a lot to this point, they change at a constant rate. So for every unit you move in the independent direction, you move a fixed amount in the dependent direction. With exponential functions, we have a percent rate of change. So for every 1 unit you move in the independent direction, you change by X% in the dependent direction, right? So that's why it's different than linear functions and how we change. So let's look at an example that sort of puts this to use so we can think about, how we might think about these different things. So this is a pretty good example that does a lot. So suppose that the 4 functions below each represent the population in thousands of a different town and how its population changes over time t in years since 2010. So we have town 1, town 2, town 3, and town 4. Okay, these are their population models. I want to know, A, which town has the largest percent growth rate? So we need to think about what R is, which again is related to A, which is in the base. So which one's the biggest? Part B, which town has the largest initial population? So that's our P naught. Part C, which town has the largest population in 2015? So you're going to need to calculate that for each town to figure out which one's the biggest. And then part D, which town is growing and which towns are decreasing in population. So again, that's related to this A value and whether or not it's greater than or less than 1. Okay, so I'm going to give you about 2 to 3 minutes. See if you can answer these 4 questions based on these 4 town models, and then we'll go through them together. Okay, take about 30 more seconds. All right. So in order to answer part A, which town has the largest percent growth rate, we need to find R for each of our models. So as a reminder, your R comes from your A value. So A equals 1 plus R. So to find the R for any of these, we would take the A value, such as 1.37 equals 1 plus R, and we would subtract 1 from both sides to get R. So here we would get 0.37. When you do 0.68 minus 1, you get negative 0.32. For the third one, when you do 0.35 minus 1, you get negative 0.65. And then finally, 1.28 minus 1 gives you 0.28. When we talk about the largest percent growth rate, I want you to think about taking all of these numbers and putting them on a number line and thinking about which one's going to be the highest on that number line. So here, positive numbers are going to be larger than negative numbers on a number line. So our solution here is that 0.37 is going to be the largest percent growth rate. Okay. For part B, we're asking which town has the largest initial population. So that means we are comparing the P0 for each of these models. So there's 250, 1200, 125, and 500. 1200 is the largest. So population 2 has the largest initial population. Okay. For part C, which town has the largest population in 2015? So remember, we're measuring since 2010. So we're really asking which one has the largest population at time equals 5, right? It's been 5 years. So we need to plug a 5 into every single model to figure out what the population is. So when you plug that into the first model, you get 1,207. When you plug it into the second model, you get 174. When you plug it into the third model, you get 0.656. And when you plug it into the last one, you get 1,718. So we can't go by initial population because some are growing and some are shrinking. So we really have to plug in a 5 for each of them. Then when we compare all those numbers, we see that population 4 is going to be the largest. So then finally, which towns are growing and which ones are decreasing? So again, they're going to be growing if our A is greater than 1 and decreasing if our A is less than 1. So we're growing in 1 and 4. And then we're going to be decreasing when our A is less than 1, which is 2 and 3. Okay. Now, we're not going to have enough time to do the other problems, the other 2 problems. I would like to give you the solution to number 4 and have you try it. Okay, you have access to the notes at home, so you can look at the graph, but I want you to make sure you can come up with this solution. So the final answer here is going to be 80 times 1.1447 to the t. So I want you to make sure you can data and the information given to get to this model, because that's sort of the last thing we need to be able to do is set up an exponential model with some data. So that's the solution. Try that at home. And if you can't figure it out, stop by Drop and Help. We're happy to go through this problem with you. Okay. Have a great rest of your week, and I will see you guys all on Thursday.